Hi everyone, and welcome to our second video, which is graphs, wherein we're going to be modeling the relationships between displacement, velocity, and acceleration. So this is going to be a bit of a longer video, so if you maybe want to skip ahead to the practice problems or go to a specific part of the lecture that would be most beneficial to you, definitely make sure to do so, and we'll have timestamps linked in the description. Okay, so let's get a move on. Okay, so we're going to be looking at three primary relationships, which is displacement versus time, velocity versus time, and acceleration versus time. So you might see that all of these graphs have a negative and positive y-axis. Why? Because displacement, velocity, and acceleration, as we learned, are all vector quantities, which means they have direction, positive or negative. So let's say an object starts at the position 0, and then it goes in the positive direction, so it moves to the right or up. So that means its velocity might be, somewhere up here. But if it was going to the left or down, it might be down here, negative. So all three of these variables, displacement, velocity, and acceleration, can be either positive or negative. And keep in mind, you might find a case where a problem says, going to the left means positive. So just keep an eye out for that. Okay, so we're going to start with displacement versus time graphs. And these graphs show the location of an object over time in a certain reference frame. So in simpler terms, some point in space is defined as 0, which is represented by the origin on the graph. Then the graph shows how many units away the object is from the origin. So for example, here would be 3, as well as in what direction. So this is right, for example, which would be positive 3. But a quick note, you might also see the term position time graphs. Those are actually the same thing as displacement time graphs, because if you think about it, an object's position is where it is in regards to their origin. So for example, if the object was here right now, it would be at position of positive 3. Displacement is how far from the origin the object has traveled and in what direction, which, again, that's positive 3. So these things turn out to be the same thing. Okay, so you try. What would the motion of the object depicted in these displacement time graphs look like? Think about that for 1 second. Okay, so for this first one, the object is actually not moving. Why? Because it's maintaining the same position, or it's staying the same amount displaced away from the origin over time, which basically means it's just staying still and not going anywhere. All right, let's look at this next graph over here. So we can see that the object is starting at the origin or the 0 position, and it's moving slowly more and more negative. It's getting more and more negative in its displacement. So we know the object is moving at the negative direction. The next thing we want to know is the slope of this graph, which is linear algebraically. Well, what does this mean? This means that the object covers the same amount of displacement over every unit in time. Let's say a second. Let's mark out some seconds here very roughly. The object is going to cover the same amount of displacement. The same amount of displacement here, here, and here over every second. Let's write that out as an equation. So our object is going the same amount of displacement over every unit of time. Now, what is displacement over time? We learned that that's velocity in basic motion. So what this basically means is that the object is traveling at a constant velocity, a constant negative velocity, as we noted earlier, because the object is getting more and more negative. So let's see our answer here. Yep, the object starts at the origin and moves in the negative direction. There's our direction at a constant speed, speed is, again, the magnitude of velocity. So yeah. All right, let's look at this next one. Take a moment to think about that. Okay, so let's note our starting position first. It's down here, so our object is starting at a negative position somewhere. Then it's slowly moving closer and closer to the origin until it eventually crosses over the origin and moves into the positive realm. So let's draw this out. Let's say this is the origin over here, and our guy Bob, for example, if he's our object, he starts over here, and then he moves slowly closer and closer to the origin. He gets to the origin, which is up here, he crosses it, and he goes into the positive realm. So which direction is Bob moving? He's moving this way, which means he's moving in the positive direction. This is regardless of the fact that he started at a negative position. He's still getting less and less negative in this first half, which means he's moving in the positive direction. Now let's look at the magnitude of his velocity. again, this object, let's erase some of the lines here. This object is moving at a constant velocity because the slope of this graph is linear, which means Bob is covering the same amount of displacement over every unit in time. So let's look at our answer real quick. Yep, the object starts at a negative position and moves in the positive direction at a constant speed, or it moves at a constant positive velocity. Alright, so now we're going to talk about graph properties, or basically what information you can glean from displacement time graphs. So first off, the slope of a dt graph. Well, we already know that the slope is change in y over change in x, which the y variable, as we discussed before, is displacement and the x variable is time. So we learned in basic motion that displacement divided by time is actually velocity. What does this mean? This means the slope of a position time graph, let's say it looks something like this, the slope of this line is actually going to be the velocity of the object. And another maybe easier way to look at this is looking at the units of each axis. So the y-axis units are meters, which is for displacement, and the x-axis units are seconds, which is for time. If you divide meters in seconds, you get meters per seconds, which is actually the units of velocity. And then a couple other quick tips to remember is that if your line is above the x-axis, you're at a positive position. If it's below the x-axis, you're at a negative position. If the slope of your graph looks something like this, a forward slash or moving up and to the right, the object is moving in a positive direction and therefore has positive velocity. But if the slope of your graph looks something like this, down and to the right, your object is moving in the negative direction and has negative velocity. And this is regardless of where your object is in position. So for example, if your object starts at a negative position, as we saw earlier, but the slope is still positive, the object is still moving in a positive direction, regardless of this bit of time when it had negative position. And then a straight horizontal line means the object is not moving, because it's maintaining the same position over time. And a straight horizontal line means the object is not moving. And actually, this connects back to what we were talking about earlier about slope, because a straight horizontal line has zero slope, which means that the object has zero velocity. Okay, now let's take a look at this special dt graph. Our object does start at the origin, and it does move in the positive direction. But what's different about this graph? It's the fact that we don't have a constant slope, which means that our velocity is increasing because we start off not that steep, and then we get a little more steep and a little more steep as time goes on. So what this basically means is that our velocity is increasing. And to show this, I've marked out the seconds. Let's say each tick mark represents 1 second on the graph. So what we're going to look at is see how much the displacement covered each second grows. So, in the first second, we travel this much displacement. Whoops, sorry. It's kind of hard to see, but you'll see better as time goes on. In the second second, we travel this much displacement, which doesn't look like this much is much greater than the first second, but it'll grow as we go on. In the third second, we traveled that much displacement. In the fourth second, we traveled that much. In the fifth, we travel this much. So as you can see, as time goes on, the amount of displacement that we move each second increases. This is velocity increasing. Why? Because velocity is equal to displacement over time. So if the amount of displacement each second is increasing, then this velocity is also going to be increasing as time goes on. But on previous dt graphs, what we did is that we found the slope on the graph in order to be able to find the velocity that an object is moving. But how do we find the velocity at an instant in time on these kind of graphs? How do we find the velocity when it's changing all the time? Now, this is a concept called instantaneous velocity, where we find the velocity at an exact point in time. So let's say, for example, somewhere over here. At this point in time exactly, what's going to be the velocity? Because it's going to be different than the second before and the second after. So basically the way you find this is you want to find the slope of the line tangent to the graph at that exact point in time. So a line tangent to a graph means that there's a line that touches the point at just that one place and it doesn't touch the graph anywhere else. So it might look something like this. There's a better example on the next slide, but it might look something like this, where this line over here, it just touches the graph at this point in time. So what we do then is that we take the slope of this line right here to find the velocity. And we're going to do a quick example on the next slide. Okay, so let's work through this example right here. We have this graph that has a non-constant slope, and we want to find the instantaneous velocity of the object at t equals 2 seconds. So I've already marked out the line tangent to the graph. So what we need to do now is find the slope of this line. So we can see here as the object moves over 1 unit, which in this case is a half of a second, it moves 2 units in displacement. Again, a half of a second, 2 units in displacement. So the change in y is 2 meters over every 1/2 second, which gives you a velocity of 4 meters per second at that exact moment in time. So now let's look at velocity time graphs. These graphs show an object's velocity over the course of time. So while in a displacement time graph, the x-axis signifies the origin or the starting position, in velocity time graphs, the x-axis signifies zero velocity, which means an object is at rest. So for some examples, let's take a couple of our previous displacement time graphs and draw the velocity time graphs for them. So with this first displacement time graph, we noted that the slope of the graph is constant, which means that the object is covering the same displacement over each unit over time. And since displacement divided by time is velocity, the object is moving at a constant velocity, which basically means the velocity is staying the same. It's not changing from some certain number. Since the object is moving in the negative direction, because the slope of the displacement time graph is negative, the velocity is negative. So the velocity time graph for this scenario might look something like this, a horizontal line below the x-axis. In this graph, the object isn't moving because a horizontal line means it's staying at the same position throughout time. So its velocity is 0 meters per second. And another way to see this is that the slope of this graph is 0. So the velocity time graph would look like this. Okay, so let's look at this graph again. Now for this graph, we determined that the displacement is increasing at a quadratic rate, not a linear rate. Now what does this mean? This basically means that the change in the amount of displacement over every second is increasing at a constant rate. Now this is a huge mouthful of words, so I'm going to actually draw out some points to show you what I mean. So over here, I've marked out some units of time. Let's just call them seconds. Now I'm going to draw out some points for you on this graph. Now starting off over here, at 0 seconds, so when the object hasn't moved yet, the object is going to be at position of 0 meters. Now, after 1 second over here, the object's going to be at a position of 1 meter. After 2 seconds, it's going to be at a position of 4 meters. After 3, position of 9. After 4, position of 16, and so forth. Now, you might recognize this. This is a parent graph for a quadratic. But what we're going to do here is we're going to mark out the amount by which the displacement has increased over each second. So what I mean by this is, let's say between 0 and 1 seconds. By how much has the displacement increased? By 1 meter. Now between 1 and 2 seconds, by how much has the displacement covered increased? That's by 3 meters. Between 2 and 3 seconds, that's 5 meters, 9 minus 4. Between 3 and 4 seconds, that's 16 minus 9 is 7 meters. Now, do you see a pattern in this increase of displacement covered over each second of time? Well, the displacement covered increases by a factor of 2 over each second. Now, what is the change in displacement over time? That's velocity, as we've determined. So, if we're saying that the change in the amount of displacement over each second is increasing at a constant rate of 2, what does that mean? That means the velocity, the change in velocity, is increasing at a constant rate of 2. I'm going to say that one more time. The change in the amount of displacement over every second which since displacement over time is velocity, this signifies a change in velocity, is increasing at a constant rate over every unit of time, which that rate is 2 meters per second. So what this really means is that our velocity is increasing by 2 meters per second each second. Now this signifies acceleration, which we'll talk about in a little bit. But the graph for this displacement time graph, the velocity time graph, will look something like this. It's not a horizontal line, but it's a linear line with a constant slope, and the slope is going to be 2 meters per second because the velocity is increasing by 2 over every unit of time. Sorry, this is missing t over here. Okay, let's go over some more graph properties, but this time for velocity time graphs. So first we're going to talk about the area under the curve of a VT graph. Now, what is the area under the curve? Say we have a graph like this, and our line for the velocity looks something like this. The area under the curve of this graph is basically the area between the line of the graph and the x-axis. So these two chunks right here, we would basically just take the sum of these chunks, and that would be our area. But you want to make sure anything under the x-axis is going to be a negative value. So really, you would subtract this value from this positive value. But what does the area under the curve actually give us? Well, the area of this section is nothing but this side length multiplied by this side length. Now, this side length is the value of the y-axis, and this one is the value of the x-axis. So what are our variables on the y and x-axis? We have time on the x and velocity on the y. If we multiply this, what does this equal? So we learned earlier that velocity is equal to displacement over time. So then velocity times time must equal displacement. So basically, the area under the curve of a VT graph gives us the total displacement that the object has traveled in that time frame. So let's say our VT graph ends here, which let's say that's t equals 7 seconds. This area basically gives us the amount of displacement the object has covered in those 7 seconds. Let's do a quick problem. Okay, so let's say this graph represents the velocity of an object, and we're trying to find the total amount of displacement it's covered in these 6 seconds. So first, let's take the area of this little portion here, which the area of a triangle is 1/2 its base, which is 2, times its height, which is also 2. So this equals 2 meters. And then we have to take the area of this portion. But remember, this is going to be negative, okay? So negative, and then let's split this up into a triangle and square. So negative 1/2 times the base of this triangle, which is 2, times the height, which is also, again, 2. So that's going to be a negative 2 meters. And then this square over here, which is side length of 2 times the side length of 2, and this is also going to be negative, so negative 4 meters. And then if we add this all together, that gives us negative 4 meters that this object traveled in total over those 6 seconds. And another super quick way to look at this calculation is just to see that these two triangles over here and here look the same area, but one's positive and one's negative, so they both cancel out, and then you can just take the area of the square to find your total displacement covered. So making quick connections like this is a skill that you want to develop for your AP exam. Okay, and now back to the second principle that we're going to talk about, the slope of a VT graph, which, as we already know, the slope of the graph is the value on its y-axis divided by the value on its x-axis. So on the y-axis here, we're going to have velocity, and then on the x-axis, we're going to have time. Now, we know from before that velocity divided by time is acceleration. So the slope of a VT graph is going to show you the acceleration that an object is undergoing. And another quick way to look at this is looking at the units. The y units are meters per second, divided by the x's units, which is seconds for time, and that equals meters per second squared, which, again, these are the units for acceleration. And now let's go over some really quick tips for velocity time graphs. So first off, if your graph is above the x-axis, then your object is moving in the positive direction because it has positive velocity. And then vice versa. If it's below the x-axis, your object's moving in the negative direction. Now, if your line has a positive slope, / like this, that means it has positive acceleration. And this is regardless of the velocity of the object. the velocity of the object could be negative like this, but since this graph has a positive slope, it's going to have positive acceleration. And we learned this could be true in the basic motion video. If an object is moving in the negative direction, but it's slowing down, that means its acceleration actually points in the positive direction. So then vice versa, if your graph is a backward slash, then you have negative acceleration. And if there's no slope, if it's a horizontal line, that means there's no acceleration because the object is moving at a constant velocity. And finally, as the graph gets closer to the x-axis, like we have over here, the object is going to be slowing down because it's approaching this zero velocity value. Even if the graph is coming from the positive direction like this, the object is still slowing down because it's going towards that zero velocity value, but it's just moving in the positive direction. And then obviously vice versa, if your graph is going away from the x-axis, that means it's speeding up. And finally, if your graph crosses the x-axis like this, that means your object has turned around. Because, for example, in this case, it started with some high positive velocity, but then it slows down and reaches this zero velocity point. And then it starts moving in the opposite negative direction and then gains velocity. So the object has momentarily come to rest and then turned around. Alright, we've been talking a lot about acceleration, so let's get on with these graphs. Okay, so as I've mentioned before, acceleration is when an object is speeding up or slowing down. Basically, its velocity is changing. We know that acceleration is change in velocity over time. So let's take a look at our previous quadratic displacement versus time graph. It looked maybe something like this, and for that, this was the velocity time graph. We've established that the object is speeding up at a constant rate, and we can see this here because this graph is linear. Since acceleration is velocity over time, this means the object's acceleration is a constant value. It's going to be the slope of this line. So it would look something like this, a horizontal line because the acceleration itself is a constant value. Now this line would be positive because our change in velocity over here is positive. Our slope is this forward slash. If our change in velocity looked something like this, or maybe even something like this, then our acceleration would be a negative constant value. Okay, so now we're going to do a little more practice, and what I want you to do is I'm going to put up a velocity time graph, and I want you to pause the video and maybe try drawing a rough sketch of what the displacement time and acceleration time graphs might look like for the velocity time depicted in the picture. Okay, so here's our first example. Pause the video right now. Alright, so let's start off by describing the motion of this graph. We start with a high positive velocity, and then we start slowing down as our graph approaches this zero, and then it hits zero, so we come to a momentary rest. And then our graph starts speeding up in the negative direction, so our object changes direction, it turns around. Now, I want to give you guys a quick reminder, the slope of a displacement time graph is the velocity. And while we know that our displacement time graph here won't have a constant slope because our velocity is changing, we can still get an idea of how steep the graph is at certain points in time. So for example, we start off with a pretty high positive velocity. So our slope has got to be positive, a forward slash, and it's going to start off pretty steep, so maybe something like this. And then our object gradually starts slowing down. It's still moving in the positive direction, so we're going to still have positive slopes, but they're going to get less and less steeper until we hit this zero velocity point where our slope is going to be just zero. We're just going to have a horizontal line at that point because our object is not moving. It's going to be at the same position for just an instant in time. And then our graph starts speeding up in the negative direction again. So we're going to gradually get steeper and steeper with our slope, and it's going to be negative now. Now, what shape, roughly, does this look like? If you're thinking parabola, you're right. Our displacement time graph is going to look like a parabola, something like this. Now, if you drew something like this or up here, you would still be correct. The position at which the graph starts and ends doesn't matter, because we don't really know anything about the position at which the object starts. What we do want to make sure you have is that the object is first moving in a positive direction, so our graph has got to go up first. And then it's going to have this little peak because the velocity is going to be 0 there. So a little peak or a vertex, if you will. And then finally, after that peak, you want your graph to move in the negative direction. You want it to move down because our graph now has a negative velocity. But otherwise, the position of the graph does not matter. Okay, I got rid of all the ink on the slide. And now our acceleration time graph is pretty simple. Our velocity time graph over here, as we noted, has a negative slope, and it's constant, it's linear, which means our acceleration is just going to be a constant negative value. So anything like this, that's a straight line underneath the x-axis, is going to be right. And ignore this little gap here. You should not have anything here because there's no negative time. But other than that, this is what your graph should look like. Okay, here's our next problem, so pause the video real quick. Okay, let's start again by describing the motion of this graph. Our velocity is constant because it's just a straight line, but it is below the x-axis, so our object has got to be moving in the negative direction at a constant speed. So our dt graph will look pretty simple. It'll have a constant slope, and it just needs to be moving in the negative direction. So again, the position that the object starts in does not matter. We could have a graph that looks like this, like this, like this, like this. All of that, any of that is valid as long as the graph has a negative slope, because that means it's moving in the negative direction. And finally, our velocity time graph has a slope of 0, so we have 0 acceleration. And this makes sense because if the velocity is constant throughout time, the object is not speeding up or slowing down, so there's no acceleration. Okay, and now as a quick last note before we move on, I want to cover scalar versus vector graphs and the biggest difference between them. Now, let me read this. A man runs at 5 meters per second to the right before turning around and running at 3 meters per second to the left. Draw the speed time graph and the velocity time graph for his motion. Now, if you can remember, what's the difference between scalar and vector quantities, or speed and velocity? Scalar quantities, like speed, they don't have direction, whereas vector quantities like velocity do. So how that distinction plays out in our graphs is that for a speed time graph, we're going to have a purely positive y-axis like this. So speed time, this is only positive. Whereas for a velocity time graph, we're going to have both positive and negative y-axis because the negative indicates the left direction. Whereas in our speed time graph, our direction doesn't matter. We're just looking at the speed of 3 meters per second, not the fact that he's moving to the left. So let's draw this out. Let's mark this as 3 and this as 5. And then over here we got 5 and we got -3 down here, which signifies the left. So our man starts by running to the right. And then he ends up running to the left, and decreases his speed to 3 meters per second. And now we can either draw the acceleration kind of going like this, or if we wanted to say that it was instantaneous, we'd instead kind of draw it like this. He changes his speed over an instant in time, which we'll look at more in our practice problems. But on our velocity time graph on this side, he starts at 5 meters per second, and then he crosses that x-axis and goes into the negative territory, negative velocity territory, and then goes at a speed of -3 meters per second, which this shows, again, the direction. He's moving to the left, whereas this just shows the change in the magnitude of velocity. Okay, now for some acceleration time graph properties, and there's not a whole lot here, but I'm going to give you the whole AP spiel. So there is such a thing as like linear acceleration, like not a flat line, but a linear line like this. And while AP doesn't expect you to quantitatively analyze this, like with numbers, because that gets all crazy, they do expect you to kind of know how the graphs for velocity and displacement might look in a situation like this. Now, the key thing to remember here is that the relationship between displacement and velocity time graphs is the same relationship between velocity and acceleration time graphs. So let's say, for example, if our acceleration is 0, like this, our velocity is also going to be 0. If our acceleration is some non-zero horizontal line like this, our velocity is going to be increasing at a linear rate like this. Now, if our acceleration itself is increasing at a linear rate, which is kind of crazy, then your velocity is going to be increasing at a quadratic rate. Now, if you think about this, if these graphs were velocity, this would be the displacement time graph. Now, if these graphs are acceleration, this would be the velocity time graph. So that's a good way to just quickly remember. Now, over here, I'm going to draw this again. Our velocity time graph would be quadratic, which, again, is kind of crazy. And then our displacement time graph would be some crazy to the power of 4 kind of stuff that I'm not going to draw out, because really that does go into calculus. But AP also expects you to kind of discuss situations in which acceleration is non-constant. Now, we're not going to cover this right now, but in later topics, some of the places where acceleration is non-constant is going to be in oscillations of springs and also elliptical orbits. And we will go more into depth in those topics, but it's still not something that you really need to have a lot of information on. Just know that those are some places where acceleration is non-constant. Okay, so now we're going to go over the area under an acceleration time graph. And we've gone over slopes and areas before, but finding the slope here wouldn't really make much sense because on the y-axis is meters per second squared and on the x-axis is seconds. So if we divide those, we get meters per second cubed, which, does anyone really know what that means? No, not really right now. So we're just going to neglect that. But the area under an AT curve does give you something of note. So area is meters per second squared, acceleration, and then time is seconds. And you multiply these out, and you get meters per second. So the area under an AT graph basically gives you the change in the amount of meters per second. So for example, if you have something like this, and you find this area over here, that would give you maybe, say if this area is 2 meters per second, that would maybe give you the change in the amount of velocity. So if you started, say, at 1 meters per second and you ended at 3 meters per second, this would give you that change. And this, again, follows the whole vein of the relationship between displacement and velocity time graphs is the same as velocity and acceleration. Because if you find the area under a velocity time graph, what does that give you? Displacement. Same, if you find the area under an acceleration time graph, that gives you velocity. So that's just a good rule of thumb to keep in mind when you're analyzing non-constant acceleration graphs. But to my belief, that won't really show up on your AP exam. And if it does, it shouldn't be past these kind of simple concepts that you can comprehend. All right, that was everything concept-wise for graphs. If you want to do some example problems, check the link in the description box and that'll take you to part 2 of this video. See you there!